it's around. It's a Hastings line.
Hello, Kavindra.
Yes, we can start.
Okay, Dr. Parth, we are going to start it now.
Okay.
Yeah. So, Namaskar. It is my immense pleasure to welcome our webinar's resource person, Professor Denker, and all the participants who have connected us online via Google Meet and YouTube channel. And this webinar is jointly organized by Department of Physics and Department of Instrumentation. Due to network problem, our college principal, Dr. Balram Pani, could not connect with us. Before starting today's webinar, I just add one or two lines. Our college name is after the renowned and 12th century astronomer and mathematician Bhaskaracharya, who is said to be the head of the astronomical observatory at Ujjain. His main work is published in many books like Lilavati and Bijganit, but his main work is on the solar system and the mathematics on the planets and their arrangement, which is available in Siddhant Shiromani. And in Surya Siddhanta, out of many observations and many discoveries, I am only mentioning only one of those. He calculated the length of the sidereal day, that was 365.258756 days, which is slightly differ from the 0.01656 modern astronomy day. So, in this remark, now I would like to invite Dr. Parth Paul. Please introduce us about the webinar's resource person. Over to you, Dr. Parth.
Thanks, Dr. Vandana. Before we start our webinar, I would like to introduce our speaker today. So we are privileged to have with us Professor Carsten Denker. Currently, he is the head of Solar Physics section of Leibniz Institute of Astrophysics, Potsdam, Germany. And he's also the head of Solar Observatory Einstein Tower in Potsdam, which has a 0.6 meter solar telescope. Professor Denker holds a double master's degree, one in physics and another in social sciences from George August University, Göttingen, Germany. He did his PhD in astrophysics, where his focus was on magnetic field of penumbral fine structures in the sun. After PhD, he moved to California Institute of Technology as a postdoctoral researcher and later as research associate for 3 years there. He joined Big Bear Solar Observatory, California as an assistant professor, and also then he was assistant professor in New Jersey Institute of Technology for 6 years. And in 2007, he came back to Germany and joined Leibniz Institute of Astrophysics, Potsdam, as a head of solar physics section. So yeah, without much further ado, I would like to invite Professor Carsten Denker to start his talk.
Okay, thank you very much, Dr. Parth, for the introduction. I need just a few clicks to get everything set up. Just a moment. Okay, I hope you can see now the presentation. Could somebody quickly confirm?
Yes, we do.
Okay, so yeah, thanks for the nice introduction. I would like to say good morning. Of course, it's only good morning here. For you, it's early afternoon. And I'm really happy to give this presentation on some of the solar physics history. Typically, when I give talks, it's about more modern solar physics, but I think it's always important to remember where we have our roots. And it's also very instructive once in a while to look back and see what other people did before us. Sometimes they did really great discoveries. Sometimes they went on erroneous paths, but I think that's also something that happens to us. And maybe a look back into history helps us also to find our way in current times. When you want to talk about history of solar physics, of course, the material that we have at our hands is very broad. So somehow we have to limit a little bit about what we are going to talk. So I will start just with a few slides about the prehistory, so the very early times, then switch to ancient Greece. And after that, we have to talk a little bit how the paradigm shifted in the observation of the solar system. And I will stop basically at the onset of modern solar physics, basically at the time at the earliest 20th century, when we had all the means at our hands to carry out solar physics as we do it today. I should also mention not all the slides are just my work. There's a very nice web page by Paul Charbonneau from the High Altitude Observatory in Boulder, Colorado, and maybe you also have a look there. But basically the composition of this talk, this is what I came up with. This is some of the pictures of some of the really very early instances where we still have buildings left telling us something about observations, not just solar observations, but also astronomy in general. So what you see here in front of you is Stonehenge, and it's a little bit tricky to date exactly when it started. So it's either 3000 to 1600 BC. And the reason for that is that the outer part that one can see as the little aubrey holes dotted around the central part of Stonehenge, it's probably older, so that probably dates back to 3000 BC. And then the inner part with these gigantic marble columns that people brought from 160 miles away to this plain here, it's a little bit more modern, if I may say so, from around 1600 BC. There is a small graphic inserted at the lower right showing you how this astronomical observatory may have looked like in ancient times. And you see there was a ring, which had some cover stones, but the most important thing were the main pillars in the interior, which are aligned, as you can see here, with sunrise and sunset at certain points during the year. And the most important times were, of course, the solstices, basically when the day and night had exactly the same time. The other stones were then used for looking, for example, planetary conjunctions or other interesting astronomical events. Before our current time counting, we had already observations recorded, and the most important ones date back from around 1375 or 1223 BC, which are actually records of solar eclipses. And the reason why this survived, it was not written at that time on paper or on papyrus, it was written on clay tables, and they've survived basically now more than 3,500 years. And so the first eclipse records we have from Ugarit in Syria. And we know also that the Babylonians started with systematic records of solar eclipse observations around the 8th century BC. We know that because these eclipse records were very important for the emperors at that time, because they either indicated favorable conditions or maybe predicted also things that were not so good. So, for example, if you wanted to start a war, then people looked that this would not fall into a time where you have a solar eclipse. And also people thought that solar eclipses might give you some information how good harvests or other things would be. So it was also important for the economy at that time. And for that reason, we have there the first records. And probably Babylonians also had some numerology to figure out when the next solar eclipse will happen. And we know, of course, the Saros cycle, our days, but there are also eclipses that appear outside the Saros cycle, so there was still space for some surprises. When we look at China, there is a famous book, the I Ching, the Book of Changes, which is basically a text mostly about cosmology and philosophy, but it also contains records of sunspots. And of course, one can ask now, okay, sunspots, don't you need a telescope to observe them? And I'm not sure if you can remember back to 2003. That was a time when we had major sunspot groups, 3 major sunspot groups on the solar surface, and they were actually visible to the naked eye. So if you looked at them early in the morning when the sun is rising, so the air mass along your viewing path towards the horizon is high, so that the sun is not as bright, one could actually see the sunspot with the naked eye without the help of a telescope. The next big step forward was to establish basically a meter stick for the solar system. And that was the first determination of the distance between the sun and the Earth by Aristarchus of Samos, and that dates back to around 250 BC. Much of our modern thinking about the solar system, but also about the sun, dates already back to ancient Greece. So it started with a cosmological model of Aristotle, who lived 384 to 322 BC. And he came up with the idea that the Earth is in the center of the solar system and also of the cosmos. And this is a geocentric model of the world and the universe. And here on the right-hand side, you can actually see the way people were thinking about it. Let me see if I can get a pointer here. No, just a second. Wait. So you can see here in the center the Earth, surrounded by the atmosphere. And the idea was that the atmosphere, air, was surrounded by fire. Reason for that are the observations of comets, where we see the tails of the comets, and people thought this is associated with the element of fire. And then on concentric circles, you see here first the moon, then you see Mercury, Venus, Earth, Mars, and then you go further out, Jupiter, Saturn, and so on. And then at the outer sphere, you see the fixed stars, which are basically unchanging in the model. And Aristotle was also the person who thought that the world and the universe consist of 5 basic elements: earth, water, air, and fire. And then he also introduced the 5th element, the quintessence, basically what holds everything together. The mathematical model describing the system was then derived sometime later by Ptolemy, and basically uses mathematical tools, knowledge about circles, to describe such a model. Now I have a problem here. Oops. Okay. So the other thing, of course, it's easy to observe beyond sunspots are observations of the solar corona, especially during the solar eclipses. But we see that the first written records that we have date back from the Byzantine times, written by the historian Leo Diaconus. And there we already basically within our time frame, 950 to 994. And so these were observations written down in Constantinople, basically Turkey, our days. Some more, how should I say it, slightly obscure hints we find actually in oracle bones. So not written records, but basically some symbolic language used in the Zhang dynasty in China, and they actually date back further, 1766 to 1123 BC. And here I have a text for you written in the Chronicles of Novgorod. These chronicles were written by monks, and they wrote actually chronicles not just of celestial observations, but also what happened during that time. So we have very accurate notes there how people lived around that time. And they write, in the evening there was an eclipse of the sun. It was getting very gloomy and stars were seen. The sun became similar in appearance to the moon, and from its horns came out somewhat like live embers. And I inserted there a picture of a solar eclipse actually observed, I think, at the Mauna Loa Observatory, operated by the High Altitude Observatory. Mauna Loa is on Hawaii. And you can actually see there a solar corona. We see the streamers along the equatorial belts, and you see the coronal holes at the north and south pole of the sun. And this is basically what people must have seen. And maybe they even report on prominences which can be seen as little red dots exactly at the limb of the sun. And there is another report from the Annales Sangalensis that the 4th hour of the day darkness covered the earth and all the brightest stars shone forth. And it was possible to see the disk of the sun, dull and unlit, and a dim and feeble glow like a narrow band shining in a circle around the edge of the disk. Now we switch back to sunspots. So we have also there official records from the Chinese Imperial Court. And we also have records basically by Theophrastus of Eresos, so from ancient Greek, describing already the details of sunspot, umbre, and penumbra. One has to go back to Aristotle. He basically claimed that the sun was a perfect sphere, and of course the perfect sphere couldn't have any dots on its surface. So people were thinking for most of the time that the sunspots were actually not a phenomenon associated with the sun, but they thought this might be the planets Venus and Mercury that just created transit in front of the solar disk. It took actually Galileo Galilei to come up with convincing arguments to say the sunspots belong to the solar surface. And we can see already here a drawing, and you can see that these drawings are more pictorial, really, and schematic than what we expect our days from the sun. So, but the idea was just to capture the main observational features. So one big sunspot in the northern hemisphere and a smaller sunspot in the southern hemisphere. And one can see again the dark umbra, the core of the sunspot, surrounded by the filamentary penumbra. Things changed with Nicolaus Copernicus. In his book, De Revolutionibus Orbium Celestum, in 1543, he basically came up with the heliocentric worldview. So he wrote, the sun is at the center of all planetary orbits, with the exception of the moon, which orbits the earth. Thus arranged, the orbital velocity of the planets decreases towards the outside, and the outer sphere of the fixed stars is at rest. In this original model by Copernicus, the Earth has three different motions. Of course, the 24-hour rotation, that is our day and night cycle, the annual movement around the sun, which basically gives us the seasons, and a precessional movement. And of course, every body that spins shows at some level precession, but here it was basically confused with the angle of the rotation axis of the sun with respect to the ecliptic, basically this plane where most of the planets orbit. And again, a very similar drawing that we had before for the geocentric world model. So here we have now finally the Earth in the center of the the sun in the center of the solar system with the proper order of the planets. And as you can see, the moon gets its own little orbit around the Earth. And this was very important. So what happens here is that we go away to say the Earth is a unique place, which is at the center of the universe. Now already the Earth has been demoted from its central role to just one planet orbiting the Sun. So basically, Sun and Earth changed their position in the universe. This was also the time when we had people like Johannes Kepler, who was able to place the orbital motion of the Earth and also of the planets into the context of a mathematical model, which we are now knowing as the three Keplers laws, describing actually that planets orbit the Sun in elliptical orbits, with the Sun being at the center of one of the focal points, or one of the two focal points of the eclipse. These ideas are laid out in three big texts. One is the Astronomia Nova, the new astronomy. The next one is the Harmonici Mundi, the harmonies of the world. And already here we see that Kepler was actually a mystician. So he thought about the mystique of the universe. He had some very romantic views how the world and the universe might work. And in this work, he tried to bring the orbital motions of the planets in the context of the scales that we have in the music. The Rudolphine tables, however, is then the first, I would say, very solid foundation of positional astronomy. Johannes Kepler actually inherited from Tycho Brahe a large volume of observations of the star and planets, and this was actually the foundation to derive the orbital motion and to derive what we know now as Kepler's law. And this he published towards the end of his life in the Rudolphine tables, and this was the basic tools for many generations to come to look into planetary motions and into positional astronomy. And it was almost an order of magnitude better than observations taken by other astronomers at that time. So what we see here is basically we are entering the era of precision astronomy. Of course, one cannot talk about the Sun without talking about Galileo Galilei. And here it's basically an animation of his sunspot drawings that he took regularly once he pointed the telescope for the first time at the Sun. Of course, he was not looking through the telescope, but he did that in projection, and then these projections were basically copied to paper. Nowadays, there's much debate if Galileo was the first person inventing the telescope or using the telescope. There are three more people, Scheiner, Harriot, and I forget one, but anyhow, who also had access to the telescope. But once you point a telescope at the Sun, you immediately see sunspots at a very good resolution. And as you can see, even from just playing these few drawings, you can see the two equatorial belts of sunspots. You can see that the Sun is rotating. In principle, you can even guess the rotation axis. And if you would plot very carefully the positions from one sunspot on one day to the next day, you would be also able to figure out that the Sun is not rotating as a solid body, but it rotates differentially. As you know, Galileo Galilei had conflicts with the Roman Catholic Church at that time, and also his sunspot observations contributed to the controversy because Aristotle's view survived in the Roman Catholic Church that the Sun has to be a perfect body. And people ridiculed him that he put basically pimples on the face of the Sun, like you will see in the face of a juvenile. And it was also a topic in his trials with the Roman Catholic Church. And so some of the information that Galileo Galilei had was actually only published towards the end of his life. Let's take another step forward. And this is work done by Rene Descartes. Some of you may actually know his work more from mathematics, but he also wrote in the Principia Philosophiae about the sun. And he was the first to point out that the sun is a very typical star. The only big difference is that most of the other stars are far, far away. So the next star from us is 4.5 light years away from the Earth, whereas the sun is only 8 light minutes away, just to give you an idea about the scale. Then basically the next thing was the Maunder minimum. As I mentioned, the telescope was invented somewhere around 1610, and one discovered sunspots. But then around 1645, people were not able to record any longer any sunspots. And even though the entire family of the Cassinis, 4 generations, observed at the Observatoire de Paris, only very few sunspots were observed. At the bottom, I have a little bit more modern plot of the sunspot numbers, and you can see from 1850 to 1700, basically there were no sunspots. Why is that important? If you go back, at least in European records, we find that this was a very cold period where even the River Thames was frozen. People were actually cutting ice blocks from the Thames for cooling basically vegetables and meat. And I don't think that any of us can remember that in recent times the Thames was frozen. And this was basically painted here by Abraham Hondius. But we also have records all over Europe that these were extremely cold times. And this is actually the foundation for space weather and space climate studies, and also plays, of course, nowadays a role when we talk about climate change and the contribution to climate change by humans, and we have to separate that from what the sun is actually doing. A more mathematical view to astronomy, but also solar physics, came by Isaac Newton. So the most known work by him is, of course, the Principia Mathematica, where he lays down the general law of gravity. But also in there, he writes how to determine the mass ratio of Sun and Earth. If you go back to Keplers laws, yes, the mass shows up in these laws, but it's not obvious if you don't have one mass to start with, how to come up with the exactly masses of Earth, Sun, or other solar system bodies. But here, Newton came already up with some idea. The original value was far off, more than a factor of 20, whereas in a second edition of the Principia Mathematica, he was already in a factor of 2 with the correct value. Okay, so we have talked now about position astronomy. We have talked about how to capture mathematical ideas about orbital motions and astrometry. The next step is really spectroscopy. So how do we extract information from the light that we receive from the sun, but also from other stars? Newton already introduced the prism. So if you have sunlight, broadband light source, and you shine it through a prism, it fans out to create the rainbow colors. But the idea of William Herschel was, okay, what is going to happen when I not just look into the visible part of the spectrum, but also in the infrared? And of course, to measure temperatures, which is basically measuring infrared radiation, you can use thermometers. And so here you see the experiment done by William Herschel. You see the visible spectrum on the surface of the desk, and then in some distance he placed various thermometers, and you also see there is one thermometer that's not illuminated by the sunlight. And this is basically just to track temperature changes in the laboratory, because if the laboratory gets warmer, you could have a false signal that then you say, okay, also in the non-visible part of the spectrum, you will see some temperature rise. So people at that time were very carefully thinking about how to do experimental setups. And here you see basically the discovery of infrared radiation. Once you start doing spectroscopy, and you can already do it with good prism spectrographs, as was done by William Hyde Wollaston, you can see that you not just get the rainbow spectrum, basically the black body radiation of the sun, but you see also that this spectrum is covered with dark lines. And it was then Josef von Fraunhofer, but also Kirchhoff and others who were able to determine where these lines actually come from. So at the bottom here you see a drawing by Fraunhofer. On the top you just see the Planck spectrum of a black body, and then at the bottom you see the location of various spectral lines. And at that time they were just labeled by letters A, B, C, D, and we know now that the D lines belong to sodium. Actually, the D lines, the sodium D lines, are a doublet, so we see there a very prominent spectral feature. And this was then experimentally validated, because the sodium lines you can also produce in the laboratory if you just use a salt, sodium chloride, and you put it in a flame. You will actually see these lines that we see on the sun in absorption, in the laboratory in emission, but the wavelengths is identical. And this is what people did then to basically determine the chemical fingerprint of the solar atmosphere, and then later on also this chemical fingerprint of other stars. And you can see here 1863 work by Gustav Kirchhoff, where the spectral resolution has increased dramatically. And now you can also see that the line identification has progressed quite a bit. So people already had at that time a fundamental understanding of atomic physics and what spectral lines might produce in the spectrum. At the same time, we still had people looking at the sun and counting sunspot, and a famous one is the German astronomer and pharmacist Heinrich Schwabe, and he was one of the most prolific observers of sunspots. So basically during his life he observed every cloud-free day the sun, and he is the one who discovered the solar cycle, that the number of sunspots actually waxes and wanes with a, as we now know, roughly 11-year cycle. He initially thought it was a 10-year cycle, but then later corrected himself. And this only happened basically starting from the wrong premises. There was the idea that there has to be a missing planet inside the orbit of Mercury named Vulcan, and he wanted to discover this planet. The other planet that people wanted to discover was a planet further out, Neptune. That was done by Joseph von Galle here at Potsdam. But the inner planet Vulcan he wanted to observe. Of course, now we know it doesn't exist. But going down the wrong path, he discovered the 11-year solar cycle. And here I have a different way of looking at this, a little bit more contemporary plot. And the bottom plot, you see the average daily sunspot area. So basically what kind of fraction of the solar surface is covered by sunspot. At the top, you see the so-called butterfly diagram, where you plot the number of occurrence, so a frequency distribution, color-coded here as a function of time and latitude. And one can see that at the beginning of the solar cycle, sunspots start out at high latitudes, then migrate to low latitude. You even have the situation when the old cycle is finishing up at low latitudes, the new solar cycle could already start at high latitudes. Johann Rudolf Wolf looked a little bit more into the details, and he invented the sunspot number, now known as the International or Zurich sunspot number. It's actually a very simple idea. We know that sunspots are clustered, so you start counting the groups of sunspots on the sun and you multiply it by a factor of 10, and then you add to that the number of individual sunspots, and that's the International sunspot number. Of course, if you observe from different observing sites with different sized telescopes, with different types of observing conditions, clouds, seeing, and so on, observations will not be comparable, but you can benchmark that. And so each observatory, each observer got a correction factor K. And of course, if you invent such a number, you claim the correction factor K equals 1 for you. But with that, you can actually bring together observations from all around the world. And this gives us now a very accurate number, sunspot number, for at least 400 years. And the reason why this number survived is it's very well correlated with the fraction of the sun covered by sunspots. So it has actually a physical meaning. It's not just a number. Around that time, people were already carrying out much more detailed sunspot drawings, so the observational techniques have improved quite a bit. So here we see a picture by Johannes Hieronymus Schröter, and this was actually input for the reconstruction of the fourth activity cycle by Wolf. Another thing I already mentioned in the butterfly diagram is the dependence where sunspots appear on the solar disk by latitude. And this is called Keplers Law. And we know that the sunspots start between 30 and 45 degrees and then move almost to the equator. Nowadays, we even know that the sunspot very near the equator might be very important because some of the magnetic flux can actually go to the other side of the hemisphere. So basically flux from the northern hemisphere can migrate to the southern hemisphere. And this might actually impact the solar cycle, the strength of the next solar cycle. So basically the work done some 100 years ago is still very important for us today. And just to give you an impression, the quality of the data people had, and they were communicating at that time. So here's a drawing of Keplers Law. You see the fat curves outlining the migration path from high latitudes to low latitudes, and in the background you see something again like the smoothed international sunspot number. So far we talked about spectroscopy and sunspot drawings, but in 1845 the first photographic pictures were taken. This is a so-called Daguerreotype, which doesn't use glass or film as a material, but basically aluminum with some chemicals. But you can see that all the details of the solar disks are captured. You see the center to limb variation, that the center is slightly brighter than the limb. You can see sunspots, and you can also discover umbra and penumbra. The most important sunspot drawing that we have is by Richard Carrington. What you see here is a big sunspot group, and the most important thing are these two little bright things indicated by A and B, because these are the first reports of a flare which took about 10 minutes. The problem was he was just looking through his telescope, seeing these brightenings on the sun, but by the time he could call somebody to also look at the same observations, the flare had already faded. But we know that this flare was geoeffective, and we know also nowadays that this was one of the strongest flares we have recorded so far, because around the world telegraph lines were actually throwing sparks We had aurora that were visible all the way down to Cuba. And the prediction would be an event like that, a Carrington event, would nowadays probably wipe out most of the satellites that we have and severely damage our technical infrastructure. It's again one of these phenomena, low chance of occurrence, but high impact on economy. And this is something we're still not well prepared for. And this is probably then also the starting point for space weather, in a sense, looking what are the adverse effects of solar activity. And associated with flares are coronal mass ejections. And now you can also see here that the observational techniques and the drawings became much, much better. So these are observations of coronal mass ejections in 1860 observed during solar eclipses. And the last thing we are missing, we had already spectroscopy. So with spectroscopy and the Doppler effect, we could already access the flow fields on the sun. So whether material is coming towards us or streaming away from us. But one thing is still missing, information about the magnetic field. Because sunspots are just the most magnificent representations of magnetic field on the solar surface. And what you see here is a picture of George Ellery Hale. And then we see a picture of a sunspot, and the dark slit that we see is the entrance to a spectrograph. And in the spectrograph, the light falling through the slit is basically spread in wavelength dimension. And this is what we see on the other side. So we see a spectrum of the solar surface with a sunspot. And in the center, you can actually see that this line is splitting up. This was already known, that spectral lines of certain elements, when you expose them to magnetic fields, will split up. That was observed by Peter Zeeman. But this was the first observation of magnetic fields on the sun. And with that, we can actually classify sunspots, and classification of sunspots allows us then to say something about how flare prolific such regions could be. And it starts with unipolar sunspots, with bipolar sunspot, complex sunspots, and so we have a whole nomenclature. But the most important thing that we get are the delta spots, where we have two umbra of opposite magnetic polarity surrounded by a common penumbra. This was actually something discovered here at the Einstein Tower by Horst Günzel in the 1950s. And we know that these delta spots are actually the most important ones for space weather effects. And we also have another classification, that is the Zurich Classification by Max Waldmeier, basically dealing with the complexity of sunspots, the size, and the separation in longitude. And this is just a classification telling us something about the growth and the decay of sunspots. Many people think that sunspots are always big. The reason for that is when we observe sunspots, of course, we like to present the most beautiful ones, but the typical sunspots typically don't get much beyond the classes C or D. So our view that we have of sunspots is a little bit skewed, but statistically they are not all that big. And with these additional information about the magnetic classes, with the information about the growth period and the morphological characteristics of sunspots, we are actually able nowadays to trace the evolution of the solar cycle in much more detail. And that's important if we want to understand how magnetic fields are generated on the sun. And this is the big new field of solar dynamo theory. And with that, I would finish my talk. What you see here is a picture taken by one of my favorite astronomy photographers, Daniel Lopez. It's taken on the Canary Islands. So you see the Taginastan, a beautiful flower. And in the background, you see the Teide, which is still an active volcano, 3,700 meters tall. And you see, of course, how the stars rotate while the Earth rotates, and you see basically the stars doing these circular tracks. And if you look very carefully, this is actually a spectrum. So the redder stars that you see here are cooler, and the brighter stars are then hotter. And this gives you already an idea how to do spectroscopy of other stars, basically just information, using information of the Planck function. Thank you very much, and I hope we have still some time for questions.
Thank you, Professor Denker, for such a informative and useful information about the solar physics. Now some questions are appearing in chat box, so I invite Dr. Kavindra. Please take some questions from the chat box. Dr. Kavindra, over to you.
Thank you, thank you very much, madam. And thank you very much, Professor Denker, for such a nice lecture. There are some questions from the participants. The first question is from Madhu Pratap Singh. What will be some examples of solar phenomena that we do not understand today?
Okay, maybe a very self-serving answer. Almost everything on the sun we do not understand at the level of detail that we want to. So I have been working mostly on sunspots. And the interesting part there in sunspots is we have nowadays numerical models, simulations, where you just use magnetohydrodynamic theory, a lot of assumptions, and you put it into a numerical model, and you create now on the computer sunspots that almost look like the ones that we observe on the sun. And the emphasis is on almost. So there are many features that are not quite right, and they also do not capture really how sunspots come into life. And I think so there's a very interesting relationship between theory, simulations, and observations. So, and with the new generation of solar telescopes, with larger and larger apertures, I think we are finally able to bring basically observations and theory together. And I think our job as people observing the sun is to keep the theorists and the people who run simulations honest. Because if nobody tells it has to look like that, you can basically simulate anything on your computer, right? So this is for me one of the interesting questions.
Another question from Chaitanya Chauhan. How do we confirm that sun is a perfect black body?
This is also, it's in principle a tricky question, because once you do measurements from the Earth, you have the atmosphere intervening, and of course the Earth's atmosphere will attenuate the solar radiation. So it's not quite easy to distinguish if this attenuation is due to the Earth's atmosphere or due to the sun itself. If you go onto satellites, you get actually more precise measurements, but also there we see that it's not quite a perfect black body. We see some deviations in the far infrared, so where the sun doesn't radiate as much as we would expect from a black body. And the other thing that hampers the comparisons are the solar spectral lines, because they take away some of the black body light and re-radiate it into a spectral line radiation, but also convert it in different spectral transitions. So especially in the UV, we have so many spectral lines that it's very hard to see the black body spectrum there.
There is another interesting question which I find. The sun is heading towards a grand minimum. So what will be the fate of Earth? Will it get colder as in times of Maunder minimum, or will it get hotter due to global warming?
Okay. Yes, there are hints that solar activity is decaying. If you look at the last three solar cycles, actually the number of sunspots is decaying, and if one would just fit a line, we go next cycle to zero. It doesn't look like that, but it's one indication. There's another indication we get from helioseismology. looking at the propagation of sound waves in the interior that also indicates that we might enter, I don't want to say a Maunder minimum, but a period of low solar activity. So that's that part of the observations. That's basically quite firm what we observe there. Now the question, how does it relate to global warming or climate change? Until the 1950s, one could clearly see the solar cycle in the climate record. One could also see the other feature that's natural, basically volcano eruptions, also leaving fingerprints in the climate record. Since the 1950s, both volcanic records and the solar record does not leave an important imprint in the climate any longer. So basically, the human contribution is so much higher. And I think at the moment there is some speculation that Maunder type minimum could produce a solar signal that could be larger than what we do as humans. But this is just a hypothesis at the moment. It's not happening. But we have to look into that. And yes, it could be possible, but then it would go that we only slow down for maybe a period of 50 years, if you take the Maunder minimum as an example, global warming. But you only slow it down. You don't compensate it. This the sun cannot do.
The next question is, what are the properties or points to confirm that sun is a star?
I think the most convincing argument is to look at spectra. So we have now high-resolution spectra, not just of the sun, but of many, many millions of stars. The most important mission was Gaia. And if you compare the spectra, then it's quite clear. They are very, very similar. And also we have nowadays models, started also something 100 years ago, of how stars are actually maintaining their form, their energy output, and so on. So this is basically the chapter of stellar evolution, stellar atmosphere, and the stellar interior. So Chandrasekhar, for example, from India, made many, many contributions there. And these models are fairly accurate. So if you compare these models with the sun, yes, there are deviations. The deviations are interesting. And if you compare these models to stars, you also see some deviations. But overall, everything fits together. And where it doesn't fit together, it's not a major thing, but it's important for us physicists to understand that, because then we get a more in-depth knowledge of stars.
Okay. The next question is, can sun's temperature be determined by sunspots? If yes, then how?
The first part of the question I didn't get. Can you repeat?
Can we determine the temperature of the sun by the sunspots?
Okay. Yes, we know basically the temperature of all surface structures on the sun. So if you look at the photosphere, where we receive most of the radiation from the sun, we know the temperature of the solar surface, something like 6,700 Kelvin. Then if you go to sunspot, the umbra, the coolest part of the umbra, is maybe some 3,500 to 4,000 Kelvin. So this part we know. But if you ask about the overall change of the radiative output of the sun, so the total energy output, that again becomes more complicated. This is known as the total solar irradiance, which is also nowadays measured by satellite. And there we see during the solar cycle variations of just a few per mil. And if you just use that change in radiative output and you put that into climate models, this is probably not sufficient to really drive climate change. So the climate change, or the impact of the sun to Earth, has to do with something more indirect. And the answer there is, if you go to the spectral irradiance of the sun, in particular to the UV, you see that there the variation during the solar cycle is much higher, factor of 10 to over 100, depending on wavelengths. And that, of course, can interact with the chemistry of the upper Earth's atmosphere. That part is not well understood. People thought for a long time it would be directly related to cloud formation on the Earth, but there is now some more doubt on that. But that's the only way really to have an impact of climate here on Earth via the UV radiation, I think.
I guess this is the last question that we can take for this webinar. The question is why the sunspots frequency got reduced over a period of time.
Can you repeat that one more time? Sorry, the connection is not that good.
Why did the sunspots detect